Okay, welcome everybody. Dr. D again. This is your Chapter 12 video. This chapter is thermodynamics. We've introduced thermodynamics before in the first semester of general chemistry, and there's some things you'll need to review. The subtitle of this chapter is Why Chemical Reactions Happen, and that's what's really powerful about this chapter and what's important about it. We're going to be able to understand why certain chemical reactions happen and others do not. Okay, so some things we're going to want to review, which are back in, I guess, chapter 10 in Gen Chem 1. Enthalpy, which we gave the note, changing enthalpy. Enthalpy is H, so changing enthalpy was delta H. Excuse me. And what enthalpy is, if you remember, it's basically heat, which we designate Q, at constant pressure. It's really just heat, but in systems with constant pressure. That's all it is. So most of what we deal with in chemistry, first normal systems that you're exposed to, simple systems, are going to be constant pressure. So we always deal with enthalpy. A couple of things that were introduced were endothermic and exothermic. So you're going to want to review these for your quiz also. Endothermic, energy absorbed. And that was delta H greater than 0. And exothermic, energy emitted. Delta H less than 0. So these are things you will need to review, things about enthalpy that you'll need to be comfortable with. Okay, so your book starts out by talking a lot about spontaneity, spontaneous processes. So the question becomes, what are spontaneous processes? And the best way to think about these is to think about, okay, well, they don't really need any continuous external source to keep them going. Once they get moving, they continue to go. Chemical reaction continues to produce products once it's started. You think about a combustion reaction, whether it be a burning fire or gasoline engine. You have to get it started. That's the spark needed to get it started. But then it continues to basically be self-perpetuating. It doesn't need any external inputs to keep it going. That's a spontaneous process. Now, it's tempting to think that, exothermic are spontaneous. And in fact, most sorry about my handwriting. Most exothermic reactions are spontaneous, but not all. And some endothermic reactions are spontaneous. So that's what we're going to get a handle on this chapter. Begin to understand why certain chemical reactions happen, why some don't, why some exothermic reactions are not spontaneous, and why some endothermic ones are spontaneous. Because I've even, stressed this point a lot. Things happen in nature to get to a lower state of energy. That's why this chemical reaction happens. That's why this happens. We're moving towards a lower state of energy. Things move towards a lower state of energy. That's only part of the story. It's an important part of the story, but there's another part of the story that helps to explain some of these exothermic reactions that are not spontaneous and endothermic ones that are. Okay, and one of the things to think about is, so for instance, ice melting. If I take an ice cube tray and put it on my counter in my kitchen, that ice will spontaneously melt, which basically means anytime we say a reaction is spontaneous, it means the reverse reaction or the reverse process, if it's just a physical process, melting of ice, not a chemical reaction, is not spontaneous. So it's not reversible without an input. So that ice is going to melt, and it's not going to all of a sudden just reform ice as long as the room stays at the same temperature. We define that room as our system along with the ice, and the ice just melts. Well, when you think about solid, liquid, gas like we see here, you think about randomness and disorder, available positions, available places for distribution of energy. That's really what this idea of entropy is in this chapter. And that's the other half of the story that explains why certain things that you might think that wouldn't be spontaneous are spontaneous, because the energy released in a chemical reaction is only part of the story. There's two types of energy. There's the energy of, if you will, the substances, but then there's the energy of motion and position. And that's really what entropy is. And you can see that here, that a gas has a lot of entropy. Okay? A lot of ability for different translational and rotational motions. A lot of ways in which the energy can be distributed. Something in a solid is very constricted and confined, so it has much lower entropy. So that's what drives something like the melting of ice. So when you look at this here, we think of, spontaneous processes. Some of them are endothermic. Baking soda and vinegar, your book uses that example. And then we just saw ice melting. And some of the keys I just mentioned, freedom of motion and state. Particles are more spread out. They have more positions. Okay, you'll see your book talk about, available microstates. But if you think about it in energy, it makes sense. Really, it is just the other energy associated with substances, not that which is actually in the bonds we're talking about, but kind of positional energy, translation, rotational energy related to motion. So we see the solid, liquid, gas increasing in motion, spreading out, more entropy. So that is this idea of thermodynamic entropy. And the second law of thermodynamics. You all know the first law. We're all familiar with that. We learned that at a young age. Energy is neither created nor destroyed. But the entropy of an isolated system always increases for a spontaneous process. That's really the second law of thermodynamics. And not the other statement is not all energy released in a spontaneous reaction is available for useful work. Okay? So we lose energy in kind of each time it transitions into another form. So this is one of those important concepts in biology with like trophic levels. You've got the small insects that eat the grass, and then, some reptiles that eat the insects, and the birds that eat the reptiles. As you move through those levels, the energy is lost each step of the way. 90% of the energy is lost. That's due to the second law of thermodynamics. Okay? So if it's an isolated system and it's spontaneous, then we know that entropy is increasing. And your book talks about defining a system, but isolated system, we talked about that in the first half of chemistry also. Doesn't exchange anything with the surroundings, basically. So you can have a thermos there or something like that. We would say that's, isolated from the surroundings. No heat is exchanged, and we talked about a closed system, so review that also. When you look at entropy then, if we say the change in entropy is greater than 0, that's basically what we're thinking about is an increase in randomness. When you think about increase in randomness, it's increasing the number of available microstates. A decrease in entropy is delta S less than 0 is a decrease in randomness. So we say, another way of looking at this is, disorder and order. A crystal, a solid. These are things that we can think about in terms of, order and disorder and randomness. Now, one way to think about this is mixing. And this works with osmosis too, and this is what we touched on with osmosis. If I have two gases separated in these two chambers, and I remove that division, these gases will randomly mix. And the reason is really a statistical reason. You can think about And in terms of a much more structured, ordered system, and this is too structured in order to stay that way, and they're going to randomly mix. But the question is really why? Well, actually, when it's mixed, there's actually more statistical probability for that. So let's take a look at it from a statistical standpoint. So here's the simplest of these. Just imagine these two gas molecules. We're going to use 4 of them. That's it. What's below there in B are the possibilities. And if you look at it, only 2 of them of the 6 will result in the gases occupying the same gas occupying the same chamber. So a separation of the gas molecules, if you will. There's lots of other options depending on how you range it. Red, blue, red, blue, red, blue, blue, red, blue, red, red, blue, and so forth. So you have more probability of it being randomly mixed, distributed throughout. And that's only using 2 marbles here, or 2 gases. Extrapolate this out to this, and you can read this in your book. I'm not going to spend time talking about it here. I just want to show the figure. Extrapolate that out, and you realize the probability now of getting this type of order arrangement becomes very small. Now think about, the numbers of gas molecules. You don't even have to think about a mole, which is, 10 to the 23rd. You can think about, a 10 to the 10. And the statistical probability of this happening becomes astronomically small. And that's why you get random mixing. Because that diffusion leads to this. The fusion of these gas molecules leads to this because, statistically speaking, it's just more probable. And it's more probable because it's kind of like more of a thermal equilibrium. In the sense that these multiple energy states, rather than confined to particular, structured system, this is very ordered and structured. So this also explains osmosis. So the third law of thermodynamics, then, is the one that basically says that the entropy of a perfect crystal is 0 at absolute 0. This is, once again, us defining a system so we can compare everything to it. And it makes sense. Absolute 0 meaning we're using Kelvin. And the most ordered thing you can think of is a perfect crystal, which means there's no mistakes in the crystal. There's no substitution of ions, which changes the structure. There's no disruption in the bonding. These things don't exist. This has 0 entropy at 0 K because there's no motion at all. As the temperature increases, you get motion, you get vibration among points. And that small vibration, all of a sudden, that you see here, can change the crystal dynamically and create a bunch of different variable states, which makes it much more random and much more disorder. So we're going to tabulate these things, and this is the way we do it. Just beware that it's 1 bar, 25 degrees C, rather than 1 atmosphere and 0 degrees C, which is what we tabulated for gases. And then you'll see tables like this, where this is just saying what is the standard entropy of a substance, of a pure substance, at 25 degrees C and 1 bar. And you can see something that's very ordered and structured has a very low entropy. Diamond, okay? Very ordered, structured substance, one of the harder substances we know because of its covalent network bonding between carbon atoms, has a very low entropy. But then you look at your gases compared to liquids, look at bromine gas compared to bromine liquid, you'll see this type of trend throughout the tables. And you have full tables in your appendices in the back of your book, which you might need to solve problems doing smart work or other things. Now, there are many factors that affect entropy. Entropy should increase with increasing temperature, right? Going to make those molecules now having more available energy states, higher energy, more motion, right? As the volume increases, you have more possibilities of positions, right? And the more particles you have, the greater the entropy. So you have 2 identical gas systems at the same temperature and volume. If the number is greater, so the pressure would have to be different. One of those has to be different because you can't have the same pressure, volume, and temperature and then number of moles be different, because number of moles are different. One of those others two has to change. But the one with more independent particles has a greater entropy because there's a greater possibility of positions and interactions and all of this, which is all part of that, kind of positional energy. So if you remember, in Chapter 10 in Gen Chem 1, we calculated enthalpy using this equation right here. This is an equation for the total entropy. There's something in the book. I'm sorry, this is not total entropy. This is just the entropy of system, just the final minus the initial. And we calculate that for chemical reactions as summing up the products minus the reactants, where n is those coefficients. So this is the exact same thing we did with delta H. So this is an equation you'll just use again to calculate the same way from tabulated values like this. The last concept in the chapter that we're going to talk about here in the video is free energy. And I just have one slide on this. We're going to talk about this right now and save the rest for lecture because it's an advanced topic. But the important statement here is that neither entropy nor enthalpy alone can predict whether a reaction is product favored. We need to consider both parts of that story. Spontaneous is another word for saying product favored chemical reactions. Okay? That's what we mean when we say spontaneous. Product favored can be exothermic or endothermic, can increase or decrease the entropy of that system. So we're going to use Gibbs free energy, which is going to mathematically combine enthalpy and entropy. And then when we look at changes in free energy between reactants and products, that does predict for us whether it's product favored. And this is the power of this chapter and ultimately of what is known as the Gibbs free energy, the ability to truly predict whether or not a chemical reaction is spontaneous and therefore product favored. And with that, that concludes the video.